Okay, today we're going to just do a short topic that helps us understand a little bit about non-permissible values for trig functions and equations. We've looked at this briefly already, but not to enough detail, so today we're just going to add this to what we've already been doing in terms of solving or proving trig identities and rearranging and so on, but we just have to be aware that there are some non-permissible values for certain situations. So this title page I have is a tan graph, so we just have regular y equals tan x. So we get a graph like that, and we already know from our graphing unit that we get some asymptote lines in between these curves. And if we actually were to check those out, these asymptote lines are at 90 degrees or pi by 2 and negative pi by 2, and then it just keeps repeating every 180, so to 3 pi by 2 and so on. So we would say in this case our asymptote lines are going to be where x doesn't exist, so we'd say x can't equal pi by 2 plus every 180, or pi n would be a good way of writing that in general form. So we've already sort of looked at this in terms of graphs, but now we're just going to do one step further and kind of think about this more algebraically. So when we're dealing with non-permissibles, what we're basically saying is we can't ever divide by 0. So if you think back to earlier math stuff, when we did rational expressions, if you had a fraction that was something like x plus 2 over x minus 3, we would simplify it to get it to that, and then we would also say x can't equal 3. Otherwise we'd have a 0 on the bottom, and we can't do that. So what's different with trig now is it's going to look similar to that, except we're going to be dealing with sines and cosines. So if I gave you something like tan x, which was our title page graph, we also know that can be written as sine over cos. So looking at this, we know that cos x then can't equal to 0, otherwise that's going to be a non-permissible value. We're going to get things that don't work. So using our unit circle, we know that cos x is 0 at 90 degrees, right? Because we'd have 1, 0 here, we've got 0 and 1 there, so our cosine value is 0, so that doesn't work. We know it also doesn't work at 270. So in this case, we would say our non-permissible values for tan x would be at 90 and 270, and then it would just keep repeating. So works the same way, but just usually we're dealing with a sine or cosine or something a little bit differently instead of just a regular value. So how we want to do this is from a graph, we would look for any asymptote lines or any breaks in the graph where it doesn't exist. But quite often what we're going to do is we're going to use just the equation and use some algebra to help us figure out where the denominator would equal to 0. And because trig graphs repeat often, so our last one we said was for tan x we can't have 90 or 270 and so on, we will often quite write them as general form. So we'd say things like 90 plus 180 n, or in radians, pi by 2 plus pi n would be our non-permissible values. Okay, so we'll just go through a couple quick examples, figure out the non-permissibles, and we'll even simplify, do a little bit of review of that, and that'll be it. So pretty short one today. So here's our first equation. We've got cosecant equals cotan over cos, so let's actually prove this as well as figure out our non-permissibles. So if we look at just the cosecant part, we know that's equal to 1 over sine. And if we look at the other part, we've got cotan, so that's cos over sine. Oops, sine theta, not x. And we're dividing that by cos. And let's put it as cos over 1, just to kind of help us out a little bit. So let's figure out our non-permissible values at this point. So on our left-hand side, we have sine. So sine theta is going to equal to 0 when our angle is 0 or 180, and so on. And if we look at the other side, we've got sine on the bottom again for the top part. So that doesn't work. We've already got it covered, so we don't worry about that. But we're also dividing by cosine, so we have to figure out where cosine is not equal to 0. And that's going to be at 90 and 270 and so on. So in degrees, we would just say our non-permissible values then are at 90 plus 90n, or we can just say 90n would be a good enough way of doing every possible non-permissible. So pretty simple, just keep doing your same thing you've always been doing, but just for questions that ask it, we need to worry about the non-permissibles as well. So for this question, we can just finish it off by canceling out our cosines. So So we have 1 over sine on the left-hand side, and we get 1 over sine on the right-hand side as well. So we've proved it, and we've got our non-permissibles. Okay, let's try another one. So we've got, this case we're not proving anything, we just want to simplify and figure out the non-permissibles. So we've got tan x on top, so let's change that to sine over cos. We've got cosine, so that's cos. Let's write it over 1 to help us out. And then on the bottom we got 1 over cos, and cotan is cos over sine. Okay, so at this point let's do our non-permissibles. So we have cosine on the bottom again, so that'll be 90 and 270, and so on. We look on the bottom, we got cos on the bottom, we've already taken care of that. We've got sine on the bottom as well, so then we're also going to get 0 and 180 and so on. So just like the last time, we would say instead of 90 plus 180, we just have every 90 degrees, so just 90 degrees n, and they want this one in radians, so we'd write it as pi by 2n would be our non-permissibles. Okay, so x can't equal any multiple of 90 degrees or pi by 2. And that's it. So let's simplify this one a little bit further. So we've got our cosine top and bottom we can cancel. We've got another cosine top and bottom that we can cancel. So we'd end up with sine x over 1 on the top, divided by 1 over sine x. Those don't cancel, so what we would get is sine squared. So our simplification is sine squared, but sine, like this sine squared by itself has no non-permissibles, but if we look at the original function, it ends up being at every 90 degrees. So this would be a good example to try graphing, and if you graph the original, it's going to look like a sine squared graph, except it's going to have spaces at every pi by 2. Okay, so if you put this in on your calculator, if you have a newer version, the older versions won't show it, but if you have a newer version, and you actually graph the original, like sine squared x, you end up getting sort of, it looks sort of like a sine graph, but it's just raised up a little bit, it looks sort of like that. But if we actually graph the original on a good version of the calculator, what it does is it actually has a blank, so the graph goes up, has a little bit of a space there, goes down. It's hard to see on the x-axis, but there's also a little space there, and it just keeps doing that. So you get these little missing spots in the graph. So the original graph has some non-permissibles. Our answer doesn't. Sine x squared is totally fine. So if you graph these, especially on a newer calculator that has the different colors, you can actually see this show up a little bit easier. All right, so that's it for that one. Let's do one more maybe. So with our next one, our last one here, we've got sine 2 theta over cos 2. So here's another one where it's pretty tough to do this with non-permissibles the way it is. So let's do some simplifying first. So if we simplify our top, sine 2 theta is 2 sine cosine, and on our bottom, we got cos 2 minus 1, so we're going to have to pick the right one to rearrange again. So if we do that, we get, let's just see here, let's pick the right one. So we want cos 2 minus 1. So if you pick the right equation, you bring the 1 over, the cos 2 minus 1 should equal negative 2 sine squared. So that's our equation there. So looking at that now, and let's even rewrite this a little bit differently. We have 2 sine on the top and cosine. Let's write our bottom as negative 2 sine and sine again. So writing it like that, you can see 1 would cancel, the 2's would cancel, so we end up just getting negative cos over sine, which would be negative cotan would be our final answer. But when we're doing our non-permissible values, let's do it from this stage before we cancel. So all we have on the denominator is sines for both. So for sine, we have it so that our angle can't equal when sine is equal to 0, and it doesn't matter because they're both 0. So we would get 0 and 180. So we just write our answer as 180n. This one's in radians, so let's put it as pi n. And that's it.